Hey AP Calc, it's Mr. Ford. I'm back with the second half of this video, starting with 832E. This one's going to be kind of advanced also, just in how we approach it, so just try to follow along. We're dealing with the... I'm going to get lunch all over my screen here. The integral from 0 to pi over 2 of the tangent of x over 2. Now, we don't have a straight formula whose antiderivative or whose derivative is just tangent. So the way we're going to do this is actually with a u substitution. We've actually done it before on a couple of different assignments back in the day, but we're going to rewrite the we're going to rewrite the tangent as the sine over the cosine of x over 2. And then we're going to use a u substitution. And the tricky thing about this u substitution is that we're going to have to make u equal to the cosine of x over 2. And the reason why is because the derivative of u is going to be the negative 1/2 sine of x over 2. I'm just doing the chain rule in my head also. The 1/2 pops out from the derivative of x over 2. And it's negative because the derivative of cosine is negative sine. And this means that negative 2 times du will equal the sine of x over 2 dx. And there's your u substitution. Sine of x over 2 dx is right there. Cosine is on the bottom of the fraction. And so now we can actually do our substitution. We've got 1 over u du. We should put a negative 2 in front of this thing too. And before we go any further, we should figure out what our new boundaries are. U of 0 is the cosine of 0, and that is 1. But u of pi over 2, that's going to be the cosine of pi over 4. Since we're looking for the cosine of pi over 2 divided by 2 is what we decided our u was. And the cosine of pi over 4 is the square root of 2 over 2. So that's our new boundary up here, square root of 2 over 2, which is less than 1. We should keep that in mind when we do our calculation, but not that it matters too much. The antiderivative of the 1 over u is the natural log of the absolute value of u. So we got negative 2 times the natural log of the absolute value of u. And we're going to evaluate this from the square root of 2 over 2 to 1, like that. We're just going to plug in those numbers and subtract. So negative 2 times the natural log of the square root of 2 over 2 minus the natural log of 1. The nice thing here is the natural log of 1 is 0. So that is just the natural log of square root of 2 over 2 times 2. There is some algebra that we could do with use properties of logarithms. I'm not too worried about it, honestly, here. I'm trying to think how I could think about this. I'm good with this answer just the way it is. I like it. I'm done with it. Let's circle it. Let's move on. 833. Again, we have a no calculator challenge. Given that function there, we're going to determine all the values where f of x is concave up. Translation there, we're going to find all the places where f double prime of x is greater than 0. So this is the same challenge, and we've seen this a bunch of times this year, is that if you're looking for concavity to be up, you're looking for the second derivative to be positive. So that's going to come down to making a sign chart. We have 1 minus x over x minus 3. I'm going to move all the way up to the side here. 1 minus x over x minus 3. We're looking for when this is greater than, or when the second derivative is greater than 0. What's going to be a pain about this is actually finding that second derivative. So for the first derivative, we're going to need to use the quotient rule. That is the original bottom times the derivative of the top, which is negative 1, minus the original top, 1 minus x, times the derivative of the bottom, which is positive 1. And that is all over x minus 3 squared. And if we shake this out and think about it algebraically, that's going to be a negative x plus a 3 minus a 1 plus an x. And so the x's are actually going to cancel out, and 3 minus 1 is 2 over x minus 3 squared. So this is going to be 2 over x minus 3 squared. And I'm going to prefer to think about this as 2 times x minus 3 to the negative second power, because that's going to make it a lot easier for our second derivative to come in because we do not need to do the quotient rule again now that we have it kind of as a polynomial right there. So if I was going to do that derivative, it would be negative 4 times x minus 3 to the negative third power times 1, which you don't need to write down because times 1 is just times 1. That's the second derivative, I believe. And so the next part is, when is this greater than 0? Or we should think about places where it's undefined. So the first thing you can do is divide the negative 4 over. Although if you do that, you got to think about, okay, when is this greater than? Another way to think about this is when is 0 greater than 1 over x minus 3 to the third power. Well, I don't know when this equals 0, but I do kind of know that if this bottom is negative, then the whole thing's negative, and if the bottom is positive, then the whole thing's positive. So really we're just kind of thinking, okay, when is x minus 3 greater than 0? Really is what this shakes out to be. Or, sorry if I got my signs correct, when is x minus 3 less than 0? That happens when x is less than 3. I believe that's the answer to the question, which kind of makes sense, because if you plug in a number that's less than 3, you're going to get a negative number right there. Oops, undo. You're going to get a negative number right in here if you plug in a number less than 3 there, and that will be a negative times a negative, which makes it positive, which makes it greater than 0. So that's my answer for that question. Moving on into the next one, we got 84. Set an integral that can be used to calculate the volume of the solid to obtain the region defined about the x-axis and or about the y-axis. And the nice thing is we don't need to actually calculate it. If you're reading the directions, all we got to do is set it up. That's pretty common on the AP test. You don't actually have to evaluate it. You just got to set it up. Now, the first thing we really got to do here is just wrap our heads around what this looks like. This is x less than or equal to 25 minus y squared. So it's going to be one of those sideways parabolas. Sorry. Having lunch. What kind of drugs? I'm out of room. So. So I'm sort of thinking of points that work on this problem. I know that if y is 5, then we're going to have a 0 inside of their thing. So x is 0, y is 5 is on this graph. I know that's true. I do know that if y is equal to 0, then x is 5 is on this graph. So 4, 5 right there. I know that if y is equal to 1, then x is the square root of 25, which is square root of 24, which is nothing. I know that if y is equal to 3, 3 squared is 9, 25 minus 9 is 16, and the square root of 16 is 4. So 4, 3 is on this graph. X is 4 and y is 3. And I think what this is going to be is it's going to be, because 3, 4 will also be on this graph. It's going to be kind of a curve like this. And we're looking for this shaded area right here. So the challenge of this problem, really after wrapping my head around that, the challenge was to calculate the volume of the solid obtained by revolving this region defined about the y-axis. So we're going to need the washer method for this, because if we do this, we're going to have a washer that'll look something like this. Kind of like that. And it really helps to think about the rectangles going on in this problem there. So the inside rectangle is always going to be 3, because that's not changing, because that vertical line of 3 is. And the outside rectangle is going to be the one that's changing, and that is determined by the graph that we have, where x equals the square root of 25 minus y squared, like that. The nice thing is that we're just going to go from, I believe if we're slicing this horizontally, we got to start at 0 and go all the way to 4, because I believe that the point 3, 4 satisfies both equations. So what we're going to have for our integral here is we're going to have the integral from 0 to 4. Our outside, we're going to put a pi in front. Our outside radius is the square root of 25 minus y squared minus our inside radius, which is 3 squared gy. And I'll put that all in its own parentheses there. And I would not go any further than this. I know that the squared right there, if I'm pointing at it correctly, where can I point correctly here? I know there's a squared right there that cancels out the square root. I don't care. The job was to set it up, and so I think we set it up. That's it. I don't think it's necessary to go any further with this one. So Kara just walked in, so you can say hi to yourself if you want to, Kara. Question 835, is there some c in the interval from 0 to 1 for which f of x equals x squared minus x, where f prime of c is equal to 0? Well, we got to justify that answer there. What we're looking for here is some sort of mean value theorem application, because I see a derivative there. Let's look at, let's think about this for a minute. Since we have the original function, and we're talking about the slope here with f prime, let's think about the slope. Let's think about what f of 1 minus f of 0 over 1 minus 0 would be. F of 1 in this problem would be 0, 1 minus 1, and f of 0 would also be 0, which is 0, over 1, which is equal to 0. So the average value on this range from 0 to 1, the average is 0. Which means that at some point, according to the MBT, this I'm going to say yes. The mean value theorem, I'm going to abbreviate that to MVT, which you can do also, guarantees that there is some c on the range from A to B such that f prime of c is equal to the average, which is f of b minus f of a over b minus a. This is literally what the mean value theorem says, as long as it's continuous and differentiable, which it is. So this is one of those mean value theorems where you calculate the slope using the two endpoints. You are going to have a derivative somewhere in there that equals that slope. And finally, we're going to look at one last question, which is setting up for kind of the last case here. Linda has enrolled in a ceramics course, is concerned about having enough clay to complete her projects listed below. She decides to calculate the volume of each object by using slicing. Which direction should she slice, and which type of cross-section should she use to evaluate the volume of her projects? So a vase, I'm thinking of a vase that looks kind of like this, where it's like maybe something like that. I think in that case, it makes sense to slice it horizontally. And I think the cross-sections would be circles. So I think this is a circle problem. Circle, and I'm going to put the word horizontal on there. I'm going to write right over my picture because I did not think about how to map that out. For a pyramid, this is kind of tricky, but a pyramid has a square base. It's got triangular sides, but the base is always a square. And so I think, again, we should slice it horizontally. And when you do that, what you'll get is you'll get a square every time inside of your cross-section. So again, for B, I think horizontal and squares. And for a rolling pin, which again, I think, I'm just thinking about the cylinder part of it. I know there's like handles on it too. But the handles are usually also little mini cylinders there. I think it would make sense to slice this vertically. And if you do that, you would get circles. So I think vertical and circles makes the most sense here. Pretty cool. Got it all done before we had to start class. So I'll see you guys in the next video. Don't forget, you are awesome.